give a warm welcome to Joe Stevens, who leads infrastructure engineering at Ascend. Joe is here discussing one of the most pressing topics in the world of data engineering, which is cloud costs. The advent of cloud computing means companies can scale their data operations more than ever before, but that sometimes comes with a significant increase in those costs. But while here there be dragons, fear not. Joe is here to shed some light on the topic and how Ascend can help mitigate those costs. Without further ado, let's hear from Joe about the gory details of network storage, computing failures, and how Ascend can help reduce all of those associated costs. Take it away, Joe.
Thanks, Carissa. Hey all, thanks all for attending the summit and my talk here. And let's just jump right into it. So kicking this off, I would like to drop in a quick poll for just everyone present. How much are you going to deal with cloud costs? So we've seen a lot of pressure around the industry, and how much are you all seeing pressure to reduce the actual cost of your data pipelines? I'll just give you a moment to go ahead and get your answers in. And I think we'll go ahead and end it there. So yeah, everyone strongly agrees. I'm not surprised. We've heard rumblings that people are interested in reducing costs, and we get it. We're all in the same economic climate. We all understand that there are pressures to reduce your costs associated with processing or just costs in general. And so we are here to help. So let's go ahead and dive in. At the top, we're going to talk about your actual cloud costs and data processing, how to mitigate those costs, and in particular, how we help you mitigate those costs and what savings are actually on the way. So not everything is present today, but we are continuing to work on new features to reduce your cloud costs as well. I am just going to give a quick intro. So for what actually drives cloud costs? What is the makeup of these cloud costs? I do have some data here from a reference pipeline that we run for our own production. It actually backs all of our billing usage information. So I'll be giving you percentages of what the cloud costs are that we see based upon that. That pipeline has a frequent regular data ingest, refreshing about every 30 minutes at a fairly high volume. I apologize, I do not remember record counts or data volume offhand, but it is a meaningful volume. So let's break it down. The first big thing that actually drives your cloud costs is going to be storage. You're dealing with a whole bunch of data. You have to store that data somewhere. In order to reference it, it must exist. It must be referenceable. What we see in our own production pipelines is that storage at scale drives around 30% of your total cloud costs. Next, as you shift toward compute, this is just all of the things that are responsible for actually processing your data, whether that is a read connector pulling in data from the outside world or from just some other storage system, or whether you're performing transforms. In this case, we'll be focusing on the Spark transforms that are run in the K8s cluster managed by Ascend, SQL, PySpark, that we're currently seeing that land around 20% of the total cloud bill. And then lastly, well, not quite lastly, but the last big pillar would be networking. And this is where you'll see another 30%. This is all of the, how do you actually get your data from A to B? Are there any associated costs during your actual processing as you are moving data around? And just all of the things that go into that. If you are moving data, the clouds tend to want to, similar to the IRS, get their cut and take a tax on any time you are moving that data around. The last one, which is a little bit more subtle, retries. So anytime you are processing data, there is some likelihood of failure of processing that data. And in that circumstance, you will need to retry. These costs will vary, but you will find that jobs tend to fail at the worst possible time. I don't say this just because I am Murphy, but Murphy's Law does still apply. The worst thing can happen, will happen at the worst possible time. So anytime you can avoid that, great. I am going to give a quick caveat. So cloud cost is a broad category. It can constitute the costs relating to your self-hosted Ascend environment, if you are self-hosted. It can constitute the data plane backend. This would be your Snowflake, your Databricks, your BigQuery, actual compute and storage plane. We do a whole bunch of work to optimize the actual data plane compute. However, for this talk, and particularly for the area that I am most focused on personally, I'm going to focus on the cloud costs related to your Ascend environment in Amazon, Azure, and GCP. So jumping in, storage. Storage is cheap. Why are we talking about it? Storage is cheap, but it does have a dastardly tendency to grow on you. The actual rates that you see, we'll be focusing mostly on blob storage because that is where we'll do the vast majority of bulk storage, with the exception of when your data plane backend is a Snowflake BQ DBX, where it'll be there. But for blob storage costs, you're typically going to be running about 2 cents per gig per month. This will vary by cloud and region, but you're generally going to be in that ballpark. And the trick with storage is that it's actually quite hard to reduce. So the nuance here is, if you are computing something and you're running a long job, you can delete a VM. That's fine. Deleting VMs, very straightforward. I do it all the time. It's great. In order to actually stop the cost of storage, you need to delete the underlying objects. And doing that requires you to know whether or not you need those objects, which is not straightforward. We do a lot of that automatically. So we will go ahead and prune any objects that you don't need, but going past that gets harder. And if you delete something, getting it back means regenerating it, assuming you can regenerate it. So how are we actually going to help reduce these? The first one, many of you are probably already familiar with: intelligent tiering and Autoclass. So in Amazon and GCP, there are functionality for automatically over time reducing the actual cost of your storage. In Amazon, this is intelligent tiering. In GCP, this is Autoclass. Unfortunately, there is not a similar feature in Azure. But what you'll see from this is that the storage costs for data not accessed for 90 days drop up to about 80%. And ahead of that, I believe actually 30 days, it drops by about 50%. The actual cost will be driven by your data usage patterns. So the way that these work is that they look at the actual activity of read on these objects, and any objects that are idle for a long time. So if you have some kind of a, let's say, an audit kind of pipeline where you're generating a whole lot of audit activity, and you're mostly just persisting it because it has to exist in case it's eventually accessed, you should see all of that transition at a fairly steady pace into colder storage and cost you less over time. Anything that is in a more active pipeline that is, being actively worked on, or that is just getting rewritten frequently, you won't see the same level of drop. So this is just one of the tools in the tool belt. There are lifecycle policies in Azure, but the specific reason that intelligent tiering and Autoclass are a straightforward option here is that there is no penalty for accessing things from cold storage. So we can safely bring these in, And if you have that audit pipeline and you then need to go and perform an actual audit and query against all of that data, you will not then be punished on the cost side. So you won't be charged for those actual lookups, which is quite important because that can get expensive and basically nuke the actual difference of that cost pretty quickly. Stepping on forward, this one's pretty exciting. We've had asks for this from a number of customers for a while. We are looking into bringing it in soon. This is Ascend Views. So the story with Ascend Views is there will be a new view component which just allows you to actually transform your data without persisting it. This will both reduce your end-to-end processing time, because rather than performing persist steps in the middle of your pipelines, as would normally occur in today's components, you'll have the option of skipping that and basically chaining together a whole bunch of different transformations to get to your end components without the additional persist steps in the middle. So improved performance and also eliminating that underlying storage costs. It does obviously have the trade-off that you won't get that caching layer for those components because of that lack of persistence. So it'll be up to you to decide where this is most appropriate, but this will be an option that you'll see before too long. No timeline announced just yet. Next up on the docket, compute. So what actually goes into compute? Compute is driven primarily by VMs. You will see that the prices of these VMs do vary, and that'll be by cloud, by region, by instance type, spot versus on demand. Even, within a given region and instance type, the spot price itself will fluctuate. So a lot of variability there. One of the things that can impact your overall cost as well is the packing and efficiency. So in an ideal world, really for all of your processing, you would like to be using exclusively spot instances, which is your cheapest purchase point, at 100% utilization. So every single core, every single gigabyte of memory, fully utilized 100% of the time. Unfortunately, the real world is messy. So in real world processing, you will run into poor packing, fragmentation. So this will be, let's say you have a multi-distributed Spark cluster running on a bunch of nodes, running across more than one node for an extended period of time. Maybe that's the only thing running, but it's doing work this whole time. So you can't actually tear down the Spark cluster, but it's not fully utilizing the node that it's running on. And this results in fragmentation of those resources. You would rather have them run together on the same node, but in this circumstance, they may not. Another, nuance here is the actual compaction of compute resources is tricky. And what this gets into is you may have experienced running microservices or stateless things. Typically moving around stateless services is pretty easy, because ultimately all you do is you just make sure that you have enough running. You can terminate one, it moves somewhere else, and there's no real world impact because there is no state. In something like a long-running Spark job, there is state. So you have whatever is in memory, whatever is in disk spill for the executors, whatever is going on with the driver. There's a number of different things that if you terminate Spark resources during the course of a job, you may lose progress against whatever you've been processing. And if you've had a, say 100 Executor Spark job running for 12 hours, and you start deleting things and you have really long running tasks, that can get pretty expensive pretty quickly. So it can end up being more expensive to try and compact it than it is to just let it finish, which just makes it a bit harder to compress the overall cost. So how do we deal with these problems? There's a couple things. Spot compute. So we have actually always run Spark on spot nodes. We've been doing this for years and years. What you'll see is you can theoretically get up to 90% of savings over on demand. In the vast majority of cases, we run a lot of these. We're typically seeing that you get about a 1/3 discount. So you'll see in the range of 60 to 70% discount relative to the price of on-demand instances, which is great. It just happens. Nothing required on your part. It'll all just work. Pod packing. So this gets a little bit into the nuances of the actual control or compute plane that we're running on top of with Kubernetes. By default, Kubernetes is optimized to run stateless services. So what you'll see is that the actual behavior of scheduling will optimize for the uptime of those services. And so it will attempt to spread them around the available compute, so the available nodes. Coming up soon, the ability has arrived to actually change that scheduling behavior and ensure that rather than spreading out the actual workloads for stability, to pack those same pods for efficiency. We have also done a lot of work to ensure that that is something that can safely be done, because there are reasons that the default behavior is what the default behavior is. So I'll go into later slides around how we ensure that that is still a safe behavior to do. Next one, idle executor preemption. So this will be on the way soon, but one of the advantages that we have with our place in the control plane is that we have an actual core understanding of what jobs are running and when. So we can look at your Spark cluster and say, we know what's running. We can actually inspect the Spark workers, the Spark executors, and we can find when a Spark executor is idle and not processing anything. And we can actually mark it as eligible for compaction. So this allows us to take advantage of the information we have on the application side, because we understand the actual data processing that you're doing when it's happening. And we can use that in order to ensure that as these Spark clusters continue to run, let's say they're staying, awake for 5 minutes in case there's another job that comes up in that period, we can go ahead and make sure that those Spark executors aren't keeping up VMs that they don't need to be keeping up. We're projecting this should be able to deliver about 50% reduction in compute costs when you're running at small volumes. So particularly when you're looking at that possible fragmentation that I mentioned earlier across a small number of nodes with a small number of pods, this should significantly help with those scenarios to ensure that you can get back down to your minimum level of compute. Next big one, Ascend Gen 2 processing with data planes. So in the Ascend Gen 1 compute model, all jobs were given their own containers to run in. This did provide great isolation. So this allowed very strong guarantees that for any given component, it would only have access to the things that it needed to have access to do in order to process the job that it was expected to process. It turns out this was actually more isolation than customers wanted. And what we found was that the more common model people were expecting was something more similar to a warehouse model, where a given compute entity has some set level of access across many things. So as we've shifted away from the Gen 1 model to the Gen 2 model, that different level of isolation allows us to delegate more of the actual work management, the low-level resource management in particular, to the compute engine, which allows for significant performance gains and up to a 60% reduction in cost. The big benefits here come with just giving a bunch of tasks to Spark, or actually to your data planes. So to your Snowflake, your Databricks, your BigQuery, giving them all of the work and then letting the brilliant people who work on those data planes work their magic and ensure that it can just do what it's good at, which is crunching a whole bunch of data and getting the results to where they need to be. And we just ensure it's empowered to do that. So for all of you on Gen 1, this is a big, exciting one to look at. This should also, in addition to the cost improvements, be very big performance gains as well. Next big pillar, networking. So what actually drives networking? There's a couple things. Interzone traffic is one of the big ones. So you'll see interzone traffic, you're charged actually at 2 cents per gigabyte. This may be a surprising number. You'll typically see it as listed as 1 cent per gigabyte. At least in Amazon, you're actually charged twice. There was a blog written on this because someone did the actual testing. But the nuance here is you are charged for data egress and for data ingress on the same data. So this ends up coming out at actually the same cost as a regional data transfer. At least in Amazon, my guess it probably works similar in GCP and Azure. Where does this come up? Why do we care? Spark Shuffle. Let's say you are doing some kind of a repartition of your data in Spark. Your executors are going to be shuffling data to each other. A lot of it. This may actually, the amount of data transferred in that shuffle may amount to more than the total data volume that you're processing. That would actually not at all be unusual. And that could drive up a very, very high bill very quickly. The next big one, NAT gateways. So what are NAT gateways? NAT gateways are used to actually access the internet from private nodes. So you'll have all these private nodes that are on these private subnets. They don't have public IPs, and they need to get to the public internet in order to get data. So you may be saying, hold on, I was told that cloud ingest was free. Sort of. So no, kind of yes. If you write data from the outside world directly into a bucket, that ingest is free. But if you are orchestrating a bunch of Spark jobs in order to process that data, they do need to get to wherever that data is stored. So if you're looking at the public internet for getting to that data, you're going to end up looking at 4.5 cents per gigabyte. Many of you may not be used to looking at data volumes that small, so I can translate this pretty quickly to that's about $46 a terabyte. And that adds up quickly. You add a petabyte, multiply it by 1,000. This is not unusual as a volume of data. This will apply to your data ingest from public internet, RCs, so any of your read connectors, in addition to the actual image pulls for the containers that are running all this processing. So Spark is not a small image, and you need to run it a whole bunch of times. So how do we address this? First big thing, zone affinity. So Ascend Managed Spark is always going to run within a single zone, which will completely eliminate the interzone costs related to shuffle. This is a known best practice for Spark. We did not invent it or discover it. This is just a good thing to do. And we do it. The next big one, NAT clusters. So we understand that the cost of pulling in data from external sources across a NAT gateway and getting charged at 4.5 cents per gig can be a preventatively high cost for a lot of our customers, and it could drive a outsized portion of their bill. So we are looking at ways to reduce that cost, and we think that we've got a target to potentially get up to 90% savings on those existing NAT costs. So look ahead to this one. It's in progress. Last big category, retries. Retries are fantastic. I'm a big fan. In most cases, if a job actually fails on an ephemeral failure, it just retries and then will recover. This is good. It is better than it failing. That said, the best number of retries is 0. So while retries are great, they cost you money to reprocess, any associated storage or network costs as well. Time, because it's reprocessing that takes time. You are not going to then succeed the job as quickly as you otherwise would. And additionally, triage. So people time, which as a business ultimately maps to money and time, or money and money, depending on how pure you want to be here on the economics of it. And that's all unfortunate. You don't want to have those additional spends. That said, some are unavoidable. Sometimes there is an unexpected network partition or some other thing that you just can't do anything about. But some aren't. And the ones that are avoidable, we do want to avoid. So how do we do that? There's a couple things here. I'm going to start with network encryption with Cilium. So one of the things that Ascend will do for you is ensure that all of your data is encrypted in transit and at rest. You never need to worry about that. It will always be secure. The way that we've done this in the past is by piggybacking on top of Spark's built-in encryption. The issue with that is Spark is not optimized to do that really well. Spark is not an encryption engine. It'll do it for you, but it's mostly focused on performing big data processing jobs quickly, reliably, at scale. It is not optimized for being really fantastic at encryption. So what we found is it had a tendency to fail. Not leak data, it would just hard fail at random, usually during your biggest, heaviest job, 90% of the way through the job. So that seemed like a bad situation. So we went ahead and brought in a network layer with Cilium that can do transparent encryption and that is really good at it. It uses the built-in functionality of the underlying nodes, and it just makes it all work incredibly reliably. So you don't have to worry about at the 11th hour of your job having that all fail. The next big one is disk isolation. So when you are running a Spark job and you are running low on memory, you will spill to disk. That is the standard behavior of Spark. It uses the resources available to it. When it does do that, it can produce an incredibly high IOPS load. That's just your write operations as it spills that data to disk. Because it's sharing a node with many other jobs, it can impact the actual stability of other workloads on the node. So we're now bringing in dedicated ephemeral disks to all Spark workloads in order to protect them from impacting each other. This will actually also reduce your total spend on disks at rest, because there is no additional disk required for the node itself. The node itself will be able to just have the minimum that is required in order to run the system, and Spark will mount as much disk as it needs to compute. And these are all on the way. So savings are on the way. We do have a number of these today, but we have an upcoming rollout in order to get you more of the savings mentioned above. We have not been able to fully spec out what these savings are that you will expect. But if you've been running a tally on your own bills, you should be able to line those up. So get your 80% on storage, get your reductions on compute and your reductions on NAT as they come, and you'll see a big impact. And thank you. I'm going to go ahead and open it up for questions.
So great information, Joe. Thank you for joining us. We have a few that we can go through right quick. The first question that we have is, when can we expect to have these updates roll out?
So we will be performing the first big rollout in about 2 weeks. So you'll see the bulk of these updates come along then, and you should see your bills drop shortly after.
Awesome. All right. Next question. How can I get my environment upgraded to Gen 2?
Great question. Talk to us. This one's really easy. So we will work with you through this process. We can talk you through the process of selecting a data plane. We have close partnerships with all the data planes we work with Snowflake, with Databricks, with BQ. So happy to talk to anyone about what will be a really good fit for you or what aligns well with your current processing models, and help ensure that you can get there safely and quickly.
Perfect. And then I think we have time for one more question. Why aren't the storage lifecycle updates available in Azure?
It's a great question. So I did touch on this a little bit earlier, but the nuance here is in the penalty-free reads. So in Amazon and GCP, the actual functionality for this intelligent tiering or Autoclass, whichever terminology you want to use, is fully managed. So they are going to make the decisions about when to perform the actual reduction in availability or the transitions to lower cost storage. If these were things that you wrote your own life cycles for, you're responsible for understanding whether or not you're going to access the data again, and you're penalized if you actually do access the data again, particularly with any frequency. The difference with these managed versions is that they take away that penalty. So because while we do know a lot about your data and we know a lot about your data processing, what we don't know is if you have a component that's idle now, will it be idle in a month from now, 2 months from now? And we don't want to put you in a scenario where you decide to update your pipeline and are then responsible for an outsized cloud cost purely on the basis of you decided to reprocess and we didn't expect the right thing. So if a similar functionality does become available in Azure, we would absolutely adopt it in a moment. But we do not want to put you in a situation where it's not safe for you to update your components or update your pipelines, because that should be something that's always safe for you to do.
Perfect. I love the customer focused perspective here as we're upgrading and innovating. So thank you again so much, Joe.